Well, maybe.
Or there's going to be more.
I don't know. All right. Vectors are like tools um, that you work with to solve problems, just like numbers. And numbers are like your basic set of tools to work with to solve for all kinds of math problems that we're coming up with. And then uh, at some point, regular numbers aren't enough, and so we move up to vectors. And so we have vectors as tools to help us solve problems. They're like, you can think of them as numbers, except they're a little bit extended. And so we could take that another step further and say that matrices are just tools to help us solve problems. And just like numbers and vectors, we have some basic operations for them. And so that's what chapter 2 is about. Actually, 2.1 is about your basic addition and scalar multiplication business. And then chapter 2 and the rest of them talk about the more complicated portions of matrices, which are matrix multiplication and inverses. So we're just going to brush up on a little bit of chapter 2 stuff, which I hope would be fairly obvious, and then we'll shift gears and study for our test. Yeah, so the basic matrix operations that we're going to talk about are addition and matrix multiplication, scalar multiplication, and then matrix multiplication. But before we do that, we have to get more of a grip on what it means to be a matrix and how to identify different portions of a matrix. So a matrix is essentially a an array, an array, no, a two-dimensional array. That's it. A matrix is basically a two-dimensional array of numbers. And if you're dealing with computer science, you can go beyond numbers. You can have an array of different things in there too. Or data science, you can have a matrix of strings or whatever else you want to deal with. But in any case, we're just going to be dealing with a two-dimensional array of numbers. And what we've been doing before is we've been identifying the matrix as a set of columns that we're putting together. And those vectors, the columns are really just a set of vectors. So that's what it says here in the first paragraph. We've been identifying matrices as a collection of column vectors. And so sometimes you'll see this notation where you have a square bracket and a bunch of boldface or vectors listed. And they usually don't have commas there to denote that you're just kind of putting them right next to each other, and so they look like a two-dimensional array. So we can think about that. That's one way we've been thinking about a matrix is a set of column vectors. Each of those column vectors will have components, and so then that becomes a two-dimensional array. And if we wanna identify just one element from that two-dimensional array, we have to be kind of specific on the row and the column that it lives in. And so we call that the ijth entry, where I is the row and j is the column. And so the upper left-hand corner would be the 1, 1 spot. And then if you start moving to the right from there, it's going to be the 1, 2, 1, 3, 1, 4, etc. And then you go down to the second row, that'll be the 2, 1 spot, and then 2, 2, 2, 3, 2, 4, etc. And so an important aspect of things that we're going to be looking at is the diagonal, or called the main diagonal of a matrix, and that's going to be the same row, same column index. Yeah. Oh, that would be, which one is which? Ninth row. Thanks for reading. I should change that in my notes. Keep that in mind when I'm grading. I'll keep that in mind. All right. So if the I and j are the same number, then you must be in the diagonal. And the identity matrix would have ones in the main diagonal and zeros everywhere else. I think we talked a little bit about that. That will play an important part in our matrix algebra, because in matrix algebra, we're going to talk about identities and additive identity. I think we talked about additive and multiplicative identity and stuff like that. So the identity matrix will end up being our multiplicative identity. All right. So some basic properties, kind of like real numbers. The matrix addition is commutative. The matrix addition is associative. The matrix addition has an identity, the 0, and this 0 over here is the 0 matrix. So sometimes I denote the 0 matrix with square brackets around it to say it's not just the number 0, it's not just a scalar 0, it's actually a 0 matrix. Distributive, if you distribute a scalar, and then there's also the reverse distribution where a matrix gets distributed through the scalars, and then there's some also associativity between two scalars on the outside. All right, now matrix multiplication, we'll go into that with a little bit more detail next time, but just to give you some properties, the matrix multiplication is associative. And distributive, actually distributive in two ways. And then there's also a distribution where or associative property with scalar. And this is what did I call this one? I think I call this one the additive identity. And then this one is called the multiplicative identity. And if you notice, if you compare the difference between the first set of properties with addition and the second set of properties with multiplication, do you see one glaring missing property? Kind of. This one, 0. Identity, no. What? Yeah. Doesn't have what? What's that called? Commutative property. So that's the very first important thing you should know about multiplication is, well, it's probably not the very first thing, but an important thing you should know about multiplication is that matrix multiplication is not necessarily commutative. So we've seen a lot of multiplications And you know how we take for granted that we can switch the order when we multiply two numbers. Turns out that with these vectors or these matrices, you can't just switch the order. Switching the order will give you different results. Yeah, so when you switch the order of A and then BC and then BC and A, they're different. So these results, these two results give you two different values. So it might happen that the matrix, when you multiply two matrices together and switch the order, you get the same answer. That might happen, and there's a special name for that matrix. I forgot what it's called. But there is a special name for matrices that commute, but in general, it doesn't. Cancellation laws do not hold, so the whole idea about canceling out the A doesn't always hold. Not necessarily hold. Sometimes it might, and A has to have a special property for this to be true. So for you to be able to say, hey, I want to get rid of A's and just cancel the A's out, you need A to be what's called invertible. And if A is not invertible, then AB equals AC does not necessarily, will not equal to B or B equals C. And you know the zero factor property that we learned in algebra? You know, when we factor a polynomial and we set them equal to 0 and say either this is equal to 0 or that's equal to 0. So number 3 over here says that that's not the case anymore for matrices. If you have A times B, a product of two matrices equal to 0, you can't conclude that one of them is equal to 0 or the other one's equal to 0 or both. So they could both be non-zero and then still get a 0 result. We talked about did we talk about transposes? A transpose is switching the rows and the columns of a matrix. And so we denote that by a t exponent looking thing. We'll see in MATLAB, because it's dealing with matrices, instead of putting a t or putting some other weird symbol, they have an apostrophe symbol to take the transpose of something. So a couple of properties for transposes, 4 properties here. The transpose of a transpose is the original matrix. If you add two matrices, take the transpose of them, it's like taking the transpose first and then adding a scalar multiple of a transpose is the transpose of a scalar multiple. So these 3 are fairly easy to kind of visualize, understand, I think. But the last one is a little trickier. When you multiply 2 matrices, you want to take the transpose of that. It's like multiplying the transpose of the matrices in reverse order. And remember that because it's not commutative, the order is important. So AB inside the parentheses and BT, AT outside parentheses are definitely going to look different, but the transpose is supposed to be this. So we'll see more of this next time. I guess next time we have a test, so the time after that. And so what I want to do is I want to leave this now and tell you that we have a test on Monday. So we'll do a little reviewing for the last half-hour class. All right? Well, the differential equations people have a test on Thursday, so I don't know if they would appreciate it. When's that? Oh, see, that's yesterday. That's done. All right, so I wanted to go to our Canvas page. And I keep forgetting to to assign stuff, and so like the quiz, I keep forgetting the quiz. So you have a second worksheet. It'll be due after the test, but the second worksheet uses more of MATLAB or Octave, and it actually does the row reducing business. And so uh, what I'm trying to do is I'm trying to give you examples of commands to row reduce something. And so we start off with a system of linear equations, and you have a matrix or augmented matrix. Um, and then you call these things. So the idea here is for you to just have this on a piece of paper on the side and then type this up, or you can do copy and paste. But I want you to do it line by line so that you can see the process of how this thing works. And then what it means to access a row, to switch two rows, and then basically those three basic operations, the row operations, it's being shown how to do that using MATLAB. And then I'm asking you to actually solve for a system that's different from the example that I gave. And then in the end here, there's an RREF, which reduces everything for you with the ones and zeros. And then I also have an extra thing if you want to work on this. To define functions, you can do this in MATLAB or in whatever other language you want, Python or C++ or Java. And then define, well, if you do it in those other languages, you have to create your matrix data structure so that you can work with that. Because I don't think all those languages have a built-in matrix structure. So you would need to create that, and then you can define a row swap, row scale, and row add to be these things. And then some other functions, if you're not using MATLAB, make an identity function. You can maybe do a check if it's a row echelon already, if you put it in a matrix, and then you can check somehow if it's row echelon or not, or if it's a reduced row echelon. So these are some programming ideas. If you're a computer science major, you should think about challenging yourself to do some of this stuff. If you're not, you can just forget about it. This is due Tuesday. So Wednesday before class? Should be before. I could change it to be due Wednesday before class. Anyways, what else is there? What? The exam. Yeah. Maybe. I'll get. Yeah, I need to install NumPy in mine, so it should be. But maybe I'll ask for it. So if you're in honors, and this is something that I need to talk about also next week, is if you're interested in honors or want to do an honors project, certainly a computer portion of doing something like this could qualify as an honors project. So that's something else to think about. Anyways, I'm on this page because in today's lecture was the sample problems and sample review exams, basically, that you can download. Did anybody dig through that and find it? Now, it was a secret. Sorry, I forgot to announce it. Well, that's what happens. That's what happens when I forget to announce. It's a secret until it pops up. So, what I was thinking about doing for the rest of today is to take a look at some of these problems and then, use that as our practice review. These problems have, let me make sure that they're actually downloadable. All right, it looks like it downloaded. I hope it's the right one. Let me see if it's the right one. Ah. Oh, it says spring. Oh, it's okay. Close enough. All right, so these things are multiple choice. Your test will not be multiple choice, but this would be a way for you to check your answer because the answers are at the end of the practice test. Okay, so you do this, you do it by hand. You don't don't look at the answers. Do it by hand, and then check your answers. Yeah. Um. Yeah. Haven't quite written it yet. So okay. So I think your exam will have a lot of these problems, and then maybe one page, 2 pages. I don't know, 1 page of true false questions, like 10 problems. Say it again. The true false would be more conceptual stuff, but then the others would be like hands-on working on stuff. Yes. No. So the quiz was a 4 by 5 matrix. I'm not going to get anywhere near that much. So the largest would be a 3 by 3 matrix that you would have to reduce. Yeah, I suppose so. Calculators. Yeah, you should show your work and what? Oh yeah, you can bring 1 page of notes. Back and front. All right. Let's uh let's do some problems. All right, transformations. I think they're towards the end here. So let's do some transformations and then kind of work backwards. Um, all right, 21 or 22? I don't know if they're the same thing. Let's do 21. Oh, I say 21 or 20. That's what I meant to say. All right, let's try to do a problem here. All right, we have A and B. Define a transformation from R to R by T of X equals A of X. And if possible, find a vector X whose image under T is equal to B. Otherwise, state that B is not in the range Actually, they call it image, so I don't know why they're changing this name. Image. Oh, that's it. So what we want to do is we essentially want to say is ax equal to b, and can we find a value for x? So that's essentially what this is asking for. And so we would just set it up as if it was an augmented matrix and then row reduce. Yeah, I mean, you could go through that process, but we can shortcut and say, let's just go through the augmented matrix. So we could say a x1, x2, x3 equals b, but you know that matrix is essentially going to be the same matrix augmented. And so when I said that in your exam the largest matrix would be a 3 by 3, I meant a 3 by 4, something like this. Yeah. A transformation is a function that takes in a vector and then outputs another vector. So our vector here, our vector input is something in R3. That's your domain. And then your output vector will be something in R3. And so what we want to do, I don't know, this is another way to try to think about this. This is your transformation from R3 to R3 that takes any vector in this first R3 in the domain into this second R3, which is the range. Now what they did was they defined a vector B, and then they want to know if there's another vector, and we'll call it X. Is there a vector X here that takes this transformation to that vector? Is there a vector X that goes to B if it runs through this transformation? Okay, it's like saying f of x is equal to square root of x, and then you can ask, is there an input value you can put into the square root function that would give you an answer of 4 or something? So what's your answer? 2 or 16? I don't know. Square root. It's a square root function. So 16 goes to 4. And if I said, what if b was equal to -3? Say no, you can't, because there's no function, there's no number that you can put into the square root function that would give you a -3. So, anyways, I don't want to row reduce this. Do you guys know how to use your calculator? The matrices in your calculator, row reduce? No. Well, it would be. You forget about all the theory. All right, so does everybody have a TI 83, 84? Oh, wow. So, no, you can't use your phone. You have to use an actual calculator. All right. Well, before you, I'm going to get your answer, but just to kind of even out the playing field, if you guys want to use your calculator to row reduce, because this quiz is about row reducing, you can do matrices, and I picked second function and x inverse. I think the TI-83 might be a little bit different, but I essentially clicked on matrix. Now, this again is for an 84. So if you have an 83, it might be a little bit different. So I have the key commands on the left side there. And then you could we'll just deal with matrix 1A. So I can press the number 1 or hit enter. Oh, wait, sorry. Yeah, I want to go back to the home page. Let's start over. All right, second function and matrix, and then, yeah, edit. Edit, and I got a list of matrices. I think it only goes through A through F on the 83, but if you have an 84, you have more. So let's just click on the first one. Right now it's a 1 by 1 matrix, so we can change these numbers to change it to whatever matrix we want. And the matrix we want is a 3 by 4. 3, and then enter, and then 4, enter, and then you fill in the values. 1, enter. Now, negatives, remember, for your calculator, when you want to do a negative, there's a negative sign here. Don't do the minus sign, because the minus sign is a binary operator for the calculator. All right. I think I'm wasting too much time on this. Why don't you guys just figure it out yourselves? Okay. Wait. If you go to math, where is it? Where's matrix math? Oh, here we go. So when you're ready, you just select RREF. Oh, I don't want it there. I want to go back to the home page. So second function, matrix, math, and then if you go up, you'll get there a little bit sooner, RREF. And then you put the matrix in, so you do that by second function, matrix, and then whatever matrix you want to put in there. In this case, you just matrix 1 or matrix A. And then you can close the parentheses or not, and then it's going to give you your result. Okay. The thing is, they'll give you decimals, so if you want to try to find a way to write things in fractions, hopefully you won't be dealing too much fractions. Meanwhile, Luis is going to tell us the answer here. So this is supposed to be an augmented matrix. Then we did RREF. So this is supposed to be an augmented matrix. And we have zeros times x1, x2, x3 is equal to 1. So 0 is equal to 1 in our last row. So this is inconsistent. To call on the matrix, you hit yeah, names. Just go to the names and then click on the matrix that you want to RREF. So inconsistent, that means B is not in the image. It's not in the image of T. So there's nothing that you can find in the domain that would make you hit B. That's like saying I can't put in any number into the square root function so that I can get -3. Which one? Inconsistent? Inconsistent. Come on, Randall, you can't read my writing yet? All right. Yes. Yes, if the system's consistent, you should be able to find one vector and probably only one vector that would hit that vector. Well, if you got an answer here, then you would have an answer that says 1, 1, 1 in the diagonals, and then you'll have 3, 4, or 7 or whatever. Yeah. Yes. Yeah. So you'll if this was consistent, you'll get x1, x2, x3 equals to whatever they are, and then that's going to be your vector. That's the vector that hits B when you put it into. So if we had 4, I say what number is going to get you 4 if you run through the square root function? The answer would be 16. So that's the number that would hit 4. Yeah. If that's the case, then this transformation is not technically a function, but that could happen. Yeah, that could happen like a projection. You would have a whole bunch of vectors that would go into one other vector in the output. So yeah, that's possible. So you see that the theory here is a lot more important than RREF, and so that's why I'm thinking it's not that big of a deal to use calculators or technology to find this, because that's just tedious arithmetic. All right. You want to do another? What do you call it? A transformation problem? All right. I think I had 23 and 24. Let's do number 23. It's really easy. What? I hope so. All right. Here they give us E1, E2, and E3, which is essentially I, J, K, and R3. Suppose that T is a linear transformation from R3 to R2 such that T of E1 equals 6, -3, and T of E2 is 2, 0, and T of E3 is -2, 1. Find the formula for the image of this thing. So we want to find a formula for T. We could do that, and I'm also interested in finding the formula for A, our standard matrix vector, because our standard matrix for the transformation, because it's kind of given to us already. In fact, that's probably a little bit easier to do. So although this is not part of the question, we can find our standard matrix A. And we know that if it takes your standard basis vectors, E1, E2, and E3, and sends them to these vectors, then those vectors actually make up the columns of your matrix. So that's really easy. So 6 minus 3, 2, 0, minus 2, 1. So this is your standard matrix for the transformation. So now what they want to do is they want us to figure out a formula for the image of an arbitrary x. Now, if we had actual numbers here, 1, 2, 3, we'd probably write them as a linear combination of E1, E2, and E3. We don't, so we just write it as a linear combination of E1, E2, and E3 using those vectors. So basically, x here is equal to, the vector x is equal to x1, a scalar, that's a scalar, and I'm going to put 1, 0, 0 here, but it's easier to put E1 because that's what it is, plus x2, E2, plus x3, E3. And so if I want to find t of x, which is what they're looking for, I guess I should put parentheses around the x. If they want to find t of x, they essentially want to find t of this thing, x1, E1, plus x2, E2, plus x3, E3, which is a linear transformation. So those linear transformation rules apply. We can, in addition, we can split them up, scalar multiplication, we can take out the things outside. So we have x1 TE1 plus x2 TE2 plus x3 TE3. And then you can just find out what E1, E2, or TE1, TE2, and TE3 are. So E1, TE1 is 6 minus 3. TE2 is 2, 0. And then all these are going to be multiplied by that scalar, x1, x2, and x3. And the last one is x3 times negative 2, 1. So just put them all together. I essentially have this is it's a 3 vector, 3 by 1 matrix. So your first element is 6x1 plus 2x2 minus 2x3. So that's just one scalar there that's being worked out. And then I'm sorry, this is a 2 by 1, 2 by 1 matrix. It's a 2 vector. So this is a minus 3x1, 0x2 plus x3. So that's your matrix. Okay. And I think that's all they're asking for. So if you look at this transformation and you look at this matrix, you'll see similarities and see how it fits together. Okay. Yes. All right. So we got a couple of transformations in. Should we do something else or for the last 5 minutes? What? True, false? Yeah. Oh, the STEM speaker series begins next week, right? Next week. So next week, the STEM speaker series will start, and then I'll have a place in the assignments page where you can post things up there. Yeah, you need to attend 3. Oh, and the other part that Sabrina was asking about was that, and I've done this in the past, so I'll do it. Is that if you go to more than one STEM speaker series, more than 3 STEM speaker series, anything after 3 STEM speaker series will count as 1 point towards your final exam. So, there. Yeah.
For the test, like in terms of like the calculations and like this kind of stuff, is it going to be divided like 60-40 in terms of like how much there is like weighted?
Probably
Like 50-50?
true, false.
Yeah.
No,
Maybe
no.
like this kind of like calculation.
The calculations would probably be 80 to 90% of the test, and then a small part of the test is the true false. Because the true false is pretty tricky, I've heard. So maybe we'll try one of these real quick. Oops, what happened? Actually, there's 4 here. No, what? This isn't true false. Oh, where's the true false? We're just running out of time here. Where? This one? Oh, okay. There's no W there. All right. Wait, this part's got knocked off. A vector v results when u minus v is added to the vector v. What? Is this false? So u minus v added to the vector v. So we add this to the vector v. These are all vectors. And so this would just be u. So false, adding u minus v to v results in the vector u. Did we do this in class? I felt like I did this. Oh. All right, we're out of time. So download the review, study it on your own, study it with some friends, and then you have one sheet of notes that you can bring to the class for the test. Okay. Good luck studying.